Welcome back, Chemistry 30. So in the last section, we looked at making Lewis structures, and now we'll look at how we use those Lewis structures for the different types of bonding that we'll encounter. So here we'll look at 1.2 ionic bonding, which is no stranger to you. Use the valence electrons and the octet rule to write the Lewis structures for ionic compounds and determine their formula. So of course, back in your previous science courses, we looked at tricks in order how to make ionic bondings, whether you use the old crisscross method or the balancing of charges. You were able to find what the formulas are. But now we'll kind of dig deeper to see why that in fact works. So if we look at ionic bonding, first of all, ionic bonding results from the transfer of electrons from a metal to a nonmetal. So again, metals tend to lose electrons, nonmetals tend to gain electrons. And of course, these have to be in equal amounts. So we have the formation of positively charged ions, which we call cations. So those are what happen to metals. Metals tend to lose, therefore they become positive. And anions, which are negatively charged ions. And of course, that's what nonmetals tend to do. Gain electrons to become stable. And then, of course, what we have is a scenario in which we have opposite charges attracting to form ionic bonds. So the metal loses electrons to form the cation, the positive charge resulting from having more protons than electrons. And the nonmetal becomes the anion because it has gained electrons because it has more electrons than protons. And we can see this shown by an example such as sodium chloride. So sodium, of course, it looks like this. It has one electron, so it's going to tend to lose that one, and the level below it will be considered the full outer level. Chlorine, it tends to want to gain electrons. It's easier to gain one than lose 7 to become stable. So over here we have the sodium ion. It lost one. Now a better way to draw that would be like this, kind of going with what we talked about earlier. So sodium would look like that. And the chloride, yeah, if we could get that negative and just simply put it outside here like that. There we go. Now it looks like another electron there. So let's maybe just do this. And I'll redraw it like so. So then, of course, we can see that 1 will balance with 1, so it's just simply sodium chloride. And, of course, back in Science 10 or physical science, we would have looked at, +1, -1 balance each other out, so it's just NaCl. So we kind of looked at the same way. So the number of electrons to be lost by the metal and gained by the nonmetal is determined by the number of electrons lost or gained to achieve a full octet. So sodium loses one, so that the level below it is considered full, whereas chlorine gains one. There's a rule of thumb that an atom can gain or lose 1, 2, or on rare occasions maybe 3, but usually not more than that. So sodium has 1 valence electron in energy level 3. If it lost that one, the valence shell is now energy level 2, so the level below, as I mentioned. Chlorine, having 7 valence electrons, needs to gain 1 more in order to complete its octet, so an electron is transferred from 1 sodium to 1 chlorine, making the octet for both. If magnesium with 2 valence electrons to be lost reacts with chlorine, which needs 1, the magnesium will donate 1 valence electron to each of the 2 chlorine atoms, forming magnesium chloride. So if we look at that, so we have magnesium, which has 2 valence electrons, and chlorine, of course, has 7. So if we look at what happens here, so magnesium can lose an electron, the chlorine can take that, but then again, we have 1 more here. So what could happen is I have another chlorine around, and magnesium can give its other electron to that. So what works out to be a perfect balance is if I have 1 magnesium and 2 chlorines, so that's why the formula becomes magnesium chloride. And of course, back in earlier grades, we would have treated it as, okay, magnesium is 2+, chloride's 1-. So maybe some of you looked at, we crisscross the charge MgCl2, so yes, that's how we get that. Or we could treat it as a balancing of charges. negative 1. Negative 1 gives us a total of negative 2, which balances a positive 2. But now you can go back a step and see what happens there in terms of electrons. Similarly, the one on the bottom here, the example in the bottom paragraph, we have aluminum. And let's see, we have aluminum and sulfur. Now sulfur, that's one that we did in the last section there. It's group 6, so it's going to have 6 valence electrons. So if we take a look at what happens there, we could have, this aluminum, here you go. Here you go. So that sulfur's good, but, I still have one left over here. So I might have to add another sulfur. And that aluminum gives its electron to here. But, no, I need another one. I only have one more with this aluminum, so I could add another aluminum. And there you go, sulfur. But then I have 2 extras here, so I could add another sulfur. Keep going and going and going, right? And there finally it balances out. So my formula for aluminum sulfide would be I have 2 aluminums for every 3 sulfurs. And of course how we handle that is Al is 3 plus. It gives up 3. Each sulfur gives up 2. So we could use the old crisscross here. The 3 goes here, the 2 goes here, and get the same formula. Or, of course, balancing charges. We would see we have to have 2 negative 6 here, positive 6. So we need 2 aluminums for every 3 sulfurs. But, of course, doing the Lewis structures, we can see how that all comes into play. So that's how the aluminum and sulfur work. Let's look at a couple more examples here. So using Lewis symbols, diagram the reaction between each of the following, then state the resulting compound that's formed. So if we have sodium and bromine, so sodium and bromine. Bromine, not bromine. Sodium is group 1, bromine's group 7. Where are we? Here we go, group 7. So 1 electron versus 7 electrons. So of course we can see what's going to happen here. Sodium is going to want to lose, bromine is going to want to gain. So we could see that sodium loses 1. So we should show that in our Lewis structure with the square brackets. And we have the bromine here. It's going to have a full level, right? Total charge of negative 1. And positive 1 and negative 1, those balance out perfectly. So the formula for sodium bromide is just NaBr. Easy, easy. So go to the next one. Calcium and oxygen. Calcium, oxygen. Of course, calcium is over here. It's a group 2. And oxygen, we've done that one before. It's a group 6, so it has 6 valence electrons. 1, 2, 3, 4, 5, 6. So of course calcium is going to want to lose, because it's a metal. It's easier to lose than gain. And look at that, it works out perfect. It works out perfect. So calcium is going to be losing 2. So the level below is going to be considered the full level. So if it loses 2 electrons, it's going to have 2 protons that are not balanced. And oxygen is going to have a full level. And it gained a total of 2. So if we take a look at, plus 2, minus 2, so calcium oxide is perfect, just like that calcium oxide. Of course, we're not doing anything different than you've done before. It's just that we're going back a step and seeing what's happening with the electrons. Magnesium and phosphorus. So if we look at magnesium, it is group 2. And phosphorus, it is group 5. Group 5. 1, 2, 3, 4, 5. So if we take a look at what happens there, so here you go. Here you go. Magnesium's good, but phosphorus needs 1 more. So we're going to have to add another magnesium to the mix. There you go, phosphorus. So phosphorus is good, but now I have an extra electron to give up. So add another phosphorus. There you go, but now phosphorus needs 2 more. So if I have 1 more magnesium, that will be able to satisfy the requirements here. Here you go, and here you go. So what happens there? I have 3 magnesiums. They are all considered stable. They all lost their 2 electrons. And yes, I'd like you to draw this out, showing me what's going on there. And then, of course, we have the 2 phosphorus that are full in their current level. And they each had to gain 1, 2, 3 electrons. So we can see here, to make this stable, I required 3 magnesiums and 2 phosphides. There we go, Mg3P2. Good, that's all you do. So you should be able to do the assignment, and we'll see you again.